Jai Hind to all. My name is Dr. Divya Sharma. I am Assistant Professor in Ajay Kumar Garg Engineering College, Ghaziabad. Now, today's video lecture is on non-linear application of operational amplifier Antilog Amplifier using diode and BJT. So, first, before we will start with this application, first you should know basic logarithmic amplifier using diode and BJT. So, both are used in applications that require compression of analog input signal, linearization of transducers that have exponential outputs, and multiplication and analog multiplication and division. So, this is you all know diode symbol. This is positive terminal anode and this is negative terminal cathode, or you can say PN junction. So, if we are connecting positive terminal to this anode terminal, so this is forward bias. This one is connected to positive terminal and this one is connected to negative terminal. Then this diode works as a forward bias or it is shorted. Now, if battery negative is connected to this positive terminal of this diode and positive terminal to this negative terminal, it works in the reverse bias and it is open circuit. This is the IV characteristics of this diode. In forward conduction, your VI characteristics is like this, and in the reverse breakdown, your VI characteristics of this diode is like this. Now, this is a IV characteristic of a diode. I is equal to I naught e की power Vf upon eta Vt minus 1. This is a current equation of diode. Here, I is current. I0 is a reverse saturation current, exponential Vf stands for forward voltage across diode. Now, eta is 2 for silicon and 1 for germanium, and Vt is voltage equivalent of temperature, here 26 millivolt at room temperature 300 Kelvin, minus 1. So, this is a current diode equation. So, before we will start with this non-linear application of operational amplifier, you should know the current equation because it will helps you in the non-linear application. Now, here from the previous equation, we can find out If is equal to I naught e की power Vf upon eta Vt minus 1, means we are talking about current we are finding in the forward direction. So, If forward current, Vf is forward voltage. So, here in this equation, we are assuming e की power Vf upon eta Vt is greater than 1. So, you can write down If is equal to I naught e की power Vf upon eta Vt. So, take natural log on both sides. So, ln If is equal to ln I naught plus ln e की power Vf upon eta Vt. So, ln and exponential are cancelled to each other. So, we will get here. We can solve this equation and find out Vf. So, Vf is equal to eta Vt ln If minus ln I naught. So, you should remember this equation and we have to put in when we are solving for analog amplifier using diode and BJT. So, this equation you should remember. Now, we will start basic anti-log amplifier using diode. First, we will start with this anti-log amplifier using diode, then we will start with the BJT, then we will study a temperature compensated anti-logarithmic amplifier using diode or BJT. Now, first we will start with this anti-log amplifier using diode. So, this is a circuit diagram. Here, diode is connected in the inverting terminal of this operational amplifier. Input voltage is applied at the inverting amplifier and positive terminal, non-inverting terminal of this operational amplifier is grounded. RF feedback resistance is connected in the, RF is the feedback resistance which is connected in the feedback of this operational amplifier, and we have to find out output voltage for this anti-logarithmic amplifier using diode. Now, here at this point, this point B is this one is connected to ground. So, if we have to find out voltage at this point A, so voltage at this point A means if it is grounded, here also voltage is, this one is also virtually grounded, then you can say Vf, we have to find out Vf is equal to V. So, when A point is virtually grounded, so Vf is equal to V in, and this equation already we have calculated from the previous slide that IF is equal to I naught e की power VF upon Veta Vt. Due to this virtual ground concept, VF is equal to Vin, so we can put here VF is equal to Vin. So we will get equation IF is equal to I naught V in upon e की power Veta Vt. Now here, if here is IB is nearly equal to here 0, here base current is nearly equal to 0, so we can consider IF is equal to I. So here I is equal to IF is equal to, here we have to find out IF, which is equal to VA minus, here this IF is equal to I. So I is calculated here VA minus V naught upon RF, and I is equal to IF. So IF is also equal to VA minus V naught upon RF. So this is this equation, and VA is equal to 0 due to virtual ground concept. So IF is equal to I is equal to minus V naught upon RF. So this is equation second, I is equal to IF is equal to minus V naught upon RF. Now this equation, put here in this equation 1, you will get here for the value of IF. So IF is equal to, you can see in equation first, IF is equal to I naught e की power V in upon eta Vt, and IF is equal to minus V naught upon RF. So we can equate these two equations for the value of IF. So minus V naught upon RF is equal to I naught e की power V in upon eta Vt. So this is equation. Now from this equation we can find out V output is equal to minus I naught RF e की power V in upon eta Vt, and here I naught RF is, we are assuming here I naught RF is equal to V reference. So put here V reference. So your final equation is V naught is equal to minus V RF V reference e की power V in upon eta Vt. In this analog anti-logarithmic amplifier using diode, what we have to find out? We have to find out output voltage is directly proportional to antilog of input voltage. So our purpose is we have to find out this. So here equation final equation is V naught is equal to minus V reference e की power V in upon eta Vt. Here we are getting here exponential terms. So we can say V naught is proportional to exponential function of V. It means output voltage is directly proportional to anti-logarithmic amplifier, anti-log V input voltage. So this is proved here. Now here eta and Vt are temperature dependent constant in this anti-logarithmic amplifier using diode. So what are the limitations in anti-logarithmic amplifier? Vt is temperature dependent constant. Vt is equal to T upon 11600. So there is any change in the value of temperature, then the change in the value of Vt. It means which causes change in the value of output voltage. It means output voltage not stable. Now the second limitation of anti-logarithmic amplifier is output voltage depend on ideally factor eta, that it may be 0 or 1. Dynamic range of this amplifier will reduce. So these are the two limitations, means eta and Vt are present in the final equation of output voltage of anti-logarithmic amplifier using diode. So we have to try to remove these two temperature dependent constant in further limitation, in further application. Now second is basic anti-logarithmic amplifier using transistor, that is also known as trans-diode configuration. Now here in this circuit diagram, here diode in the previous circuit, here diode is connected at the inverting terminal of this operation amplifier. So diode is replaced by this transistor. Here NPN transistor is used. So diode is replaced by NPN transistor. If base is ground, here you can see base is ground and collector is effectively grounded here. Due to this, base is grounded. Now B and A point are at the same potential according to the concept of virtual ground. So collector and base junction is shorted and transistor is equivalent to diode. Here this configuration is when we can say collector and base junction are shorted, then we can say it works as a diode, and this configuration is known as trans diode configuration. Now here also we have to find out output voltage for this anti-logarithmic amplifier using BJT. Now you all know here this transistor is used. So I, IC and I be the currents flowing through resistor R, collector C and emitter E. Now you all know I is equal to IB plus IC. So we are assuming here IB is less than IC. So I is nearly equal to I, means emitter current is nearly equal to collector current. Here transistor equation is IC, collector current is equal to saturation current is in bracket e की power VBE upon VT minus 1. So this is the transistor equation, and VB is the voltage across base and emitter of a transistor. In this equation, if we are assuming e की power VBE upon VT is greater than 1, so we can write down IC, collector current is equal to saturation current in bracket e की power VBE upon VT. And VBE from this circuit diagram, VB is equal to V input. So in place of VB, we can put here V in. So IC is equal to I naught e की power V in upon VT. And IC is equal to, this IC current is equal to I. And I is equal to VB minus V naught upon RF. And VB is equal to 0. So IC is equal to I is equal to minus V naught upon RF. And here IC is equal to I is equal to V naught upon RF. Or you can say if R is resistance is here, so you can replace RF is equal to R. So IC is equal to I is equal to minus V naught upon R. So put this equation IC in equation 1, here this equation 1, or we can equate these two equations and find out in the for the value of IC. So here minus V naught upon RF is equal to I naught V e की power V in upon VT. So from this equation we can find out V naught is equal to minus I naught RF e की power V in upon VT, and as we are assuming here I naught RF is equal to V reference. So V naught is equal to minus V reference e की power V in upon VT. So here from the if we are comparing this equation and the previous one, so eta parameter is not present here, that is temperature dependent. It means that parameter is removed when we are using anti-logarithmic amplifier using trans diode. Here from this equation V naught is directly proportional to exponential of V in, and eta is not present in the output voltage of this equation. So one limitation of anti-logarithmic amplifier using diode is overcome by this anti-logarithmic amplifier using transistor. Now the third one is temperature compensated anti-logarithmic amplifier using diode. Here this is anti-logarithmic amplifier. Here diode is connected at the inverting terminal of this operational amplifier, and this circuit is temperature compensated circuit. So it overcomes the disadvantages of anti-logarithmic amplifier. D2 here, diode D2 and D1 have matched characteristics with diode D1. Now D2 and D1 are matched in all respects. It means VT and I naught is reverse saturation current, both same, and change in them with temperature is also identical. So due to infinite impedance of A2, IB2 is equal to 0. Naturally current through D2 is I reference. So now here also we have to find out the output voltage, and we have to we have to overcome the limitations of the previous one anti-logarithmic amplifier using diode and BJT. Now here we have to find out output voltage. So this first one we have to solve this circuit diagram. So V2 is the input voltage of this anti-logarithmic amplifier, and we can find out output voltage. If we have to solve this one, then we can find out the output voltage for this circuit. So how we can find out V2? You can see this circuit diagram. V2 is the difference of inverting voltage and non-inverting voltage. So V2 is equal to V1 minus VF1, because in V1 voltage is connected at the positive terminal and VF1 is the voltage connected at the negative terminal. So we can write down this equation, V2 is equal to V1 minus VF1. This is equation 1. So in this equation, we have to find out V1 and VF1. So V1 you can find out, apply here voltage divider rule and find out V1 is equal to R2 upon R1 plus R2 into input voltage is applied at this terminal. So that is V in. So V1 is equal to R2 upon R1 plus R2 into V in. Now here we have to find out VF1. So this is diode. So diode current, by the help of diode current equation, we have found it here. VF1 is equal to plus eta Vt ln If minus ln I0. And If is equal to, here in the circuit diagram you can see IR current is equal to If current, because Ib is near, here we are assuming that is nearly equal to 0 due to virtual ground concept. Here Va is 0 and Ib is nearly, means internal base current of this operational amplifier is nearly 0. So IR is equal to If. So we can put here in place of If, we can put here IR. So VF1 is equal to plus eta Vt ln IR minus ln I0. Now this equation A and equation B, you can put these equation, means value of V1 and value of VF1, put in this equation 1 and you can find out V2. So V2 is equal to, when we'll put these two equation in this equation 1, V2 is equal to R2 upon R1 plus R2 into V in minus eta Vt ln IR minus ln I0. But here V2 is equal to, now this is the equation when we are solving this, when we are putting this A and B in equation 1. Now V2. So from this equation, V2 is equal to how much? V2 is equal to minus VF2, and minus VF2 is, V2 is equal to minus eta Vt ln V0 upon Rf minus ln I0. Now equate this equation 2 and 3 for this V2. So we can find out output voltage. V0 is equal to IR Rf ln inverse V in upon eta Vt R2 upon R1 plus R2. When we'll put equation V2 here in this equation 2, so by equating these two equations we can find out the output voltage, this one, and you can write down log inverse is equal to antilog. So output voltage is equal to IR Rf, this is reference voltage, anti-logarithmic input voltage upon eta Vt R2 upon R1 plus R2. So in this equation we can see output voltage does not depend on temperature dependent parameters I0. I0 is also a temperature dependent parameter. So in this equation we can see I0 is present, not present here. So V0 is not dependent on this I0 parameter. So Vt is still present. Therefore, temperature compensator is partially provided. To eliminate this Vt effect by making resistance divider, these are the R1, R2 resistance divider, resistances consisting R1 and R2 temperature sensitive using thermistor. So these are the applications of anti-logarithmic amplifier to obtain value of Ex, and second one is analog multiplier, and third one is obtain value of ratio from dB value. So these are the applications of anti-logarithmic amplifier, and these are the references of this topic. Thank you.